So this is problem 13 from chapter 30. Here we have a toroid that has a rectangular cross-section as shown in the figure. I'm going to draw the figure in a moment. And we are to show that the self-inductance is given by some expression. Okay? So our toroid, so this is 13. So our toroid looks like this. So normally toroids have circular cross-sections. This one has a rectangular cross-section. The drawing in the book is much better. So imagine that you have a rectangular prism and you just turn this into a torus. Okay? So maybe we make this a little bit thicker here, something like that. But this is a given number of turns, some radius, okay? Some inner radius and some outer radius, probably. So the expression that we are going to have involves the inner radius, the outer radius, the height, and the number of turns. So this is the height of each rectangle that forms this toroid, and there's an inner radius, R1, and there's an outer radius, R2. We are to find the self-inductance of this toroid. Okay? Now, how are we going to do this? Well, let's start with the definition of self-inductance. So self-inductance is a relationship between the total flux, so total flux, and the current that it carries. Okay, so the proportionality constant between the current that your circuit element carries and the total flux through your circuit element is going to be the inductance or the self-inductance of that element. So here we need to calculate phi, and to calculate phi we need to find the magnetic field. Now you can look up the magnetic field of a toroid, but if you don't remember the magnetic field of the toroid, do not panic. Okay, this is the important thing. If you see this in an exam and you don't know the magnetic field of the toroid, then you don't have to panic. What you can do is that this, you may remember, is a standard application of Ampere's law. So you draw an Amperian loop, and you'll have a circle of radius r. So the number of, we can write Ampere's law for this. Let's do it a little bit formal. 0 times I enclosed. I'm not going to go through that how we get rid of the dot product and then take B out and so on and so forth, but this comes to B times 2 pi r on the left hand side and mu0 times the number of turns times the current in each turn. Okay? So the magnetic field for a toroid is mu0 and I over 2 pi r. It's not constant. It's different from a solenoid. In a solenoid, it's constant. In a toroid, it's actually slightly different than near the inner radius than the outer radius. Okay, it's slightly stronger here than it is here. Okay, so this is our magnetic field, and of course we have to calculate the flux. Now, to calculate the flux, we can't just multiply. So flux for a uniform magnetic field is B times A. Or uniform B, but B is not uniform. B depends on R slightly. So what we need to do is that we need to divide this into little pieces. Over each piece, the magnetic field is going to be constant, and then I can calculate the flux for each little piece, and I can add these up. That amounts to an integration. And the way to divide this into little pieces is to use little strips like that. So this is probably very small, but I'm going to redraw that rectangle here. By the way, this is very similar to the previous problem, the previous suggested problem in this chapter, so you can also check that out. I'm going to have a little strip like this. This is H, and this is going to be R. And the magnetic field, dr, the magnetic field at this point is going to be given by that. So there's a magnetic flux, little magnetic flux corresponding to this. What is that? That is B times dA. This B is now constant over this little interval. The R doesn't change. It changes the infinitesimal amount. So the magnetic field is also not going to change. And this is going to be mu0 and I over 2 pi r. Now this dA is H times dr. H times dr. And now to calculate the total flux, we need to integrate this. Add up all these little fluxes, and that integration runs from R1 to R2. So if you look at this, this will be the center of the toroid. This is our R coordinate, so to say. This is where R equals R1. At the other side, R equals R2. So we integrate this from R1 to R2. And this is going to involve 1 over r. 1 over r's integral is the logarithm. Then it becomes a difference of natural logarithms, which is the logarithm of the ratios. So this is now mu0 n I h over 2 pi logarithm of r2 over r1. Now this is for flux in one of them. The total flux is going to be n times this. So this becomes n squared, and this is equal to, the total flux is equal to L times I. And so the I's go away as they should. The mutual inductance or self-inductance does not depend on current, it only depends on the geometry, only the geometrical factors. So we get mu naught n squared h by 2 pi times natural logarithm of r2 by r1, which is in fact the expression given in the book. So the proof is complete.